start recording. Okay, a couple of questions. When will quiz 12 be available? So I am going to be doing quite a bit of catching up myself this weekend. So hopefully I'll be able to roll out as much of this next 2 weeks as possible. I know that we're getting close to the end, and you folks who've been able to work ahead or at least kind of see what's coming up, I know that's been helpful to you. So I'm sorry I don't have chapter 11 fully up yet, but hopefully by Sunday we'll have the meat of that up. And just to kind of preface this chapter, it's sort of a really important piece of Calc 2, but similar to yesterday, you don't really see this again until you get to a little bit in discrete math. If you have to take discrete, like if you're in computer engineering, you probably have to take discrete. And definitely again in differential equations, but it's not necessarily something where if like Calc 3 is the end of the road for you, this stuff you might not see again. And as we go through this chapter as a whole, I think when I was learning this chapter way back in the day when I was taking Calc 2, it didn't go well for me. And here's sort of why it didn't go well. It wasn't that I think it's harder than the other stuff we learned. I think chapter 9, like our first chapter, was actually honestly one of the hardest ones. So don't let that scare you that it didn't go well for me necessarily. I think my biggest problem back when I was a student is that like I really wasn't very good at figuring out how to make decisions, but and because like I never had like practice making decisions because I'm a pretty good memorizer. So sort of like up until that point in my career, I could get away with memorizing things and not having to think actually about why I needed to use what. And so come sequences and series, which is our last chapter for Calc 2, and it's all about decisions and understanding concepts. And to me, that was it was a skill that I had never really practiced, and so it made it hard for me. But as such, I hope that like the way that we can sort of move through this together, we can highlight sort of both the concepts. I think you folks did a really great job in chapter 10 when we were looking at improper integrals that were like converging or diverging. I think we did a really good job with that, like conceptual understanding. And so I think that actually is going to prepare you folks a little bit better than maybe perhaps I was prepared, or I prepared myself rather, back when I was taking this class, okay? The little bit that we're going to do today is sort of setting the stage for next week and the week after. We're going to learn about a lot of different tests to see whether things are convergent or divergent. Okay, so today's lesson is really like, let's just warm our brains up again with convergent versus divergent. But next week, we're going to be learning a whole bunch of different tests that you can use to figure out whether things are convergent or divergent. And I think the trickier thing about next week will be deciding which test is best for this particular question. And it might be a different test for every question. That's sort of like one way to go about it. But another way to go about it is some folks pick like one or two of the tests. They really master those, and then they can get through like the bulk of the questions. And so along the way next week, you'll find certain tests that we learn are going to be sort of like they make more sense to you. And so those might be good ones to invest in. But we'll also talk about the pros and cons of all the tests. So like, what is this one good for and what are its limitations? Because there's no one perfect test, which is why we have so many that we're going to learn next week. Okay. So with that, I hope I haven't scared you away from chapter 11, but we're going to start with 11.1, infinite sequences. Okay. So a few things that we know, you may or may not have learned about sequences and series back in pre-calc. I think, again, it's sort of one of those things that like sometimes you're rushing through the curriculum and you kind of lose a few days and you just don't get to it. So we'll kind of keep it a little bit basic today. But here's what we know, that a sequence is nothing more than a list of numbers written in a specific order. Okay? And so that's what we're going to focus on for the first part of today, is that we just have a list of numbers and we're going to be exploring whether they converge or they diverge. Okay, so we're not looking at integrals like we did in the second half of chapter 3, but rather we're going to be focusing on the limits of those like we did in 10.1 and 10.2. Okay. Now, the word convergent means that the limit approaches a numerical value, and that's something that we're all pretty familiar with. And then divergent means that the limit approaches positive or negative infinity. Okay. So what's new in this section is we're going to take a look at the idea of a finite sequence versus an infinite sequence. Okay. So, for example, I'm sure while you're taking this class, it feels like it is infinitely long, like it just will never end. But in reality, it is a finite class. We have 8 weeks for it, and then it is over. Okay, so finite sequences are where it's just like part of a list of numbers. Whereas an infinite sequence, which is what we're going to be focusing on, is truly a sequence that goes on forever and ever. So whatever that pattern is, it just keeps going. And so when we look at our infinite sequences, we actually have 2 different cases. So in one case, this infinite sequence might converge, meaning that the limit of this sequence goes to a specific number. And in the other case, we will take a look at some where the infinite sequences diverge, okay, or are divergent. And we're going to look at this in a couple ways. We're going to look at it numerically. So with numbers, like how can we tell, okay, we took the limit, we got a number, it converges, or we took the limit, we got positive or negative infinity, so it diverges. Okay, so we're going to look at it numerically, and we're going to look at it graphically. Okay, so just like we looked at situations where we were like, is this getting close to the x-axis fast enough? Yes, then it converges. Or maybe it looks like it's getting to that x-axis too slowly, and so it would be a divergent sequence. We're going to go back to that same idea. Okay. Okay, so let's start with some basics. We've got this sequence, 1, 1, 2, 3, 5, 8. Anybody seen that sequence before or know what it's called?
Fibonacci.
Yes, this is the Fibonacci sequence. And in a Fibonacci sequence, how do we find the next term?
You add the 2 together and you get the next.
Yeah, exactly. So if I take 1 plus 1, I'm going to get 2. If I take 1 plus 2, I'll get 3. 2 plus 3 gives me 5. 3 plus 5 gives me 8. And so that means the next term would be 13, because I would have 5 plus 8 would give me 13. Okay? So a little notation to go here is that we have a specific way that we call each term in our sequence. So our first term is called usually a sub 1, okay? Meaning it is the first term in the sequence. That means that the next one will be a sub 2, and the next one will be a sub 3, and then this one would be a sub 4, a sub 5, a sub 6, okay? So every term has a spot, and we often use the little subscript to depict which spot it's in. And what we can say in general So A sub n, okay, so A with a little n means the nth term in a sequence. It also means that it's basically like if I put n into some function, the number that comes out is the nth term in that sequence. So if I put 3 into an equation for the Fibonacci sequence, what number should I get out?
2.
2, yeah. And if I put 6 into that Fibonacci sequence equation, what number should come out? 8, exactly. Yeah, so the number that is the subscript tells us which number term, but it's also the number we plug into the equation that we have, okay? So overall, sequences, okay, so sequences, they are like a function, okay? So what I mean by like a function is that they are similar to a function in that you plug in numbers, okay? Except they are discrete in their output, input and output. Okay. And what I mean by the word discrete is that you're not ever going to have an A sub 0.5 or an A sub 7.8 or an A sub negative 2/5. Okay. We're looking, all of our input values are always going to be positive integers. Okay, and we can see that when we look back at our Fibonacci sequence as an example, we have A sub 1, A sub 2, 3, 4, 5, 6, and all of those numbers are positive integers, okay? So what we're going to be focusing on here is this idea that it's like a function in the fact that there's an equation. However, we're limiting our input or our domain to positive integers. Okay. Can my output be a fraction?
Yes.
So my output doesn't have to be an integer, only my input. Can my output be negative?
Yes.
Yeah, okay, so the positive integer part only talks about the input. Okay, so positive integer restriction is only for the input, but for the output, you can get a variety of things, okay? All right, so let's take a look at example number 2. We've got 1/2, 1/4, 1/8, 1/16, ... And so what I'd like us to do is find a formula, or we call this one an explicit formula for the given infinite sequence. Okay, so what formula can I write so that every time I plug in, like when I plug in 1, I'm going to get 1/2. And when I plug in 2, I'm going to get 1/4. And when I plug in 3, I'm going to get 1/8. Like, what formula would get me those results?
1/2 exponent n, and then n plus 1.
2 to the negative n.
So I think Broy's got one here, which is very similar to what Mariah was saying, 1/2 to the n. Yeah, I would agree with that. Or we could say 2 to the negative n. That's certainly another way of saying it. Now, tell me what you meant by the n plus 1. I'm not really sure why you have an n plus 1.
Well, because if n is 1, then it's just 1/2. But if it's 2, it becomes a quarter. And then if it's 3, it's an eighth, because you're adding 1 each time.
Yeah, but we're just plugging in the subscript.
Okay.
Okay. All right, so we've got our a sub n equals 1/2 to the n. So with the explicit formula, what makes that different is the subscript is literally the number you plug in. You plug in 1, you plug in 2, you plug in 3. In everywhere you see the n, and you should get the corresponding fraction, okay? Now, we do sometimes put a little caveat afterwards, like any restrictions on n. And so in this case, we're actually starting with n has to be greater than or equal to 1, okay? Some of the problems we start with 1, some of them we start with 0. Sometimes there are other starting points, but 0 and 1 tend to be the most common starting points, all right? But it is important that you include that in whatever formula you're writing so that whoever's using that formula knows which number to start with, okay? So what we're gonna do in part B is we're just gonna plot a few of these points, okay? So the first point that I could plot would be, have a y value of 1/2, but what would the x value be?
One.
Yeah, it would be 1. So this little yellow number, that is our x value, or sort of our input value. And then the fraction that we get out, 1/2, 1/4, 1/8, 1/16, those are all of our sort of y values when we think about plotting them. So I'm going to make this 1/2 up here on the y-axis, okay? But on the x-axis, we're going to count, this will be 1, 2, 3, 4, 5, 6, 7, okay? So let's plot a few of these points. At 1, I'm going to plot 1/2, okay? At 2, I'm going to plot 1/4. At 3, I'm going to plot 1/8. At 4, I'm going to plot 1/16. What would I plot for 5?
1/32.
1/32, okay. And then for 6, it'd be like 1/64, and then 7 would be,
And it would it go to like infinity, I guess, since the denominator will almost be 0.
I want a number. What number do we get when we plug in 7?
Oh,
1/4.
Over what?
1/128.
1/128, yeah. So we're getting like really close down to that x-axis there. So here's the difference. When you're sketching a graph for a sequence, remember how we said the input is only positive integers? That means there's no points between the points that I drew. Like the points that I drew are the only ones that are in the sequence, along with every other whole number if I kept going out on the x-axis, all right? So what we do not want to do is now connect our graph with a curve. Does that make sense? Like we can't connect them because there are no points in between. So, but what we can do is still look at the pattern here, okay? Now this pattern here, if we go all the way out to the into the like like the end term, right? So we've got 1 over 2 to the 1 millionth, or 1 over 2 to the 1 billionth. What y value is that term getting close to?
It's approaching 0.
It's approaching 0. Okay. So based off of this picture, I noticed that it's dropping really quickly. It's getting close to 0. And then I also think, looking back at my equation, there's no way to get a negative number out. So it's not going to go below the x-axis. In fact, it's just going to get super, super close to it. Okay. So based off of the picture, we should be thinking it probably converges. Okay. But let's use limits to show that it really does converge. So we're going to take the limit as n approaches infinity of the formula that we wrote in part A, 1 over 2 to the n. And so let's go ahead, like we do with limits in general, that we should just try plugging in our number or whatever n is approaching first to see if we can just do it that way. And so I get 1 over 2 to the infinity, which is about 1 over infinity. And we know that that is not undefined because we're still taking a limit. We're just talking about what does it get really close to? And it gets really close to 0. Okay? So 0 is a numerical number. So it means that our sequence converges. Okay? Because 0, right? So it converges because 0 is a number, but also it converges to 0. Like 0 is the value that those n terms get really, really close to. Right? So the number tells us that it converges, but it also tells us the value to which it converges. All right, any questions about example 2? Okay, so let's take a look at another sequence. So I have 2 over 1, 4 over 3, 8 over 5, 16 over 7, 32 over 9. And what I'd like us to do is take a few moments and see if we can find a formula, an explicit formula, where when I plug in 1, I'm going to get 2. Where I plug in 2, I'm going to get 4/3. Where I plug in 3, I'm going to get 8/5. Where I plug in 4, I'm going to get 16/7. Okay. So take a moment to kind of play around with some different equations and see if you can't find a value.
Should we say it?
Yeah. So Kwong, I agree with you. I think that we could actually take your equation and make it even a little bit more simple. But I think we would all kind of agree that all the numerators are powers of 2, right? 2, 4, 8, 16, 32. And so on the top, we could say 2 to the n, right? Because 2 to the first power is 2, 2 squared is 4, 2 to the third is 8, 2 to the 4 is 16, 2 to the fifth is 32, okay? And now we have to figure out another way to say the bottom part using the same value of n. All right, so that's sort of the trick here. We need to define it for the same value. Whatever I put in for n in the top, also has to make the denominator true for wherever I plug in n. So Kwong, I think you had 2n plus 1 and then minus 1, or other way around. But I think we can take what you said, sort of distribute that 2 and combine some terms. And if we have 2n minus 1 on the bottom, let's see if that works. I plug in 1, I'm going to get 1. I plug in 2, I'm going to get 3. I plug in 3, I'm going to get 5. I plug in 4, I'm going to get 7. Okay? So I know that this is maybe like a little weird for some of us the first time, like how do you even come up with these formulas so quickly? And that's something that you get to study a lot more in discrete math, like coming up with these different formulas. 2 to the n is pretty common if you're looking for powers of 2. That's a pattern that we should be familiar with. But for the denominator, this 2n minus 1 is actually a really common way to say odd integers. Okay, so that's kind of like if you're thinking you're going to take discrete, that's a good little tidbit to hold on to. 2n minus 1 is a very common way of saying odd integers. Okay, so let's do the same thing where we plot a few of these points. Okay, so I know that 2 is just 2. That's fine. This 4/3 is like 1.33 if I'm graphing it. 8/5 is 1.6. 16 over 7 is about 2.28. 32 over 9 is about 3.55. Okay, so I just put those into my calculator to get some decimals so that when I plot it on this graph over here, I can make them a little bit more exact. So let's see what might be good. Maybe let's call this 1, 2, 3, and then whoop, 1, 2, 3, 4, 5. We'll go with those. Okay. So if I plot the first point, I'm going to get right here, right? That's my 2. Now, when I plug 2 into the equation, I get 1.33, so that's about here. When I plug in 3, I get about 1.6. When I plug 4 in, I get 2.28. When I plug 5 in, I get 3.55. Okay. Now again, I do not want to connect the points because when I connect them, what I'm implying is there are points between the ones that I drew, okay? But that's not true when we're talking about sequences. It is true when we're talking about functions though, all right? So what do we think here based off of our picture? Converge or diverge?
Diverge.
Diverge, and what's your reasoning for that?
Because it doesn't get close to 0.
Yeah, it looks like if I kept plotting points that they would kind of all just keep going up, right? So I think an initial guess of diverge is a great guess, okay? So let's use limits to see if we can't confirm this answer. So the limit as n approaches infinity of 2 to the n over 2n minus 1. And so let's do as we normally do. We plug in the infinity, see if it needs to be like require any other strategies to simplify it. Because like maybe like number 2, maybe we don't need anything else. But 2 to the infinity is going to give me infinity. Actually, let me write this out. 2 to the infinity and then 2 infinity minus 1. 2 to the infinity is going to be infinity. 2 infinity is going to be infinity. Okay. So when we see this, all right, and this was a concern that I had on exam 2, I believe it was. Some folks were like, oh yeah, this is 1. And they would continue simplifying and say this is 1. Okay. we cannot say that, especially in this case, because the numerator is an exponential, which means it grows way faster than the linear function on the bottom, okay? So this part right here is a no-go. But, and I'm not sure that I was clear enough the first time, if you feel like you need to use L'Hopital's, which we do here, you need to show me this step that you got infinity over infinity, or you got 0 over 0. Otherwise, like, how do I know that you know when to stop taking derivatives of the top and bottom, right? Like, or why you need to use L'Hopital's. So we have our infinity over infinity, which means we can use L'Hopital's. So we're gonna take our derivative of our numerator and our denominator. The denominator is a lot easier in this case. Derivative of 2n minus 1 is just 2. Derivative of 2 to the n, we don't see that often, but it is 2 to the n times natural log 2. So whatever the base is, if it's not e, then we have to write like natural log of that base. Now we've taken a derivative. If you just keep taking a derivative, then it shows me you don't really understand when to use L'Hopital's and when not to, okay? So every time you take a derivative, plug in your bounds or plug in your infinity again and see if you get a value. So we get 2 to the infinity natural log 2 over 2. This is going to give us infinity over 2. Do I need to use L'Hopital's again?
No.
No, right? Because that's not infinity over infinity or 0 over 0. So this does simplify to infinity, which means that our sequence diverges, as we correctly guessed, based off of the graph above, okay? So remember, when we're looking at the limits for sequences, it's nothing more than the y value of what the explicit formula is going towards when we go to infinity, okay? Now, one nice thing about sequences is because our input is limited to positive integers, we never have to check negative infinity and worry about maybe additional signs. We're really only concerned about the positive end because that's where the infinite sequence is headed towards. Okay, let's take a look at example number 4, okay? So this time, in example 4 and example 5, I've given you the explicit formula. Now, the ability to find an explicit formula is definitely tricky. So if you were like struggling a little bit in example 3, like how did you find that formula? It just takes a lot of practice to kind of do it. And there's no real, like, there are some things I can suggest you try, like for odd numbers, 2n minus 1, or for even numbers, 2n, but it's not always so cut and dry, okay? So our focus is gonna be more on like this conceptual piece, like the graph, does it converge, does it diverge? So for this question, I'd like us to find the first 4 terms, meaning I'd like you to find a sub 1, and then I'd like you to find a sub 2, a sub 3, a sub 4. Okay, so for finding a sub 1, we've got 1 over 1 minus 2 times 1. Okay, because everywhere I see the n, I just plug in the subscript. And I can simplify this a little bit. I get 1 over 1 minus 2, or negative 1. That means that on my graph, I can go ahead and plot the point 1 comma negative 1, okay? So let's make negative 1 down here. And so my first point will be right there. So let's go ahead and find a sub 2, a sub 3, and a sub 4. So when I plug in 2, I'll get 2 over 1 minus 4, which is negative 2/3, and if I want to graph that, that's about negative 0.66. If I plug in 3, I get 3 over 1 minus 6, or negative 3/5, which is negative 0.6. When I plug in 4, I get 4 over 1 minus 8, or negative 4/7. And if we use a decimal approximation, we'll get about negative 0.57. Okay. Now, a really important note here, if you're only writing the sequences, like if you don't have to graph it, never turn things into decimals. If it comes out as a fraction, leave it as a fraction. Okay, so these decimals that I'm writing on the side are only so that we can graph our points, not because that's how you would write the sequence. If you were going to write the sequence, I would expect to see -1, -2/3, -3/5, -4/7. Okay, the other ones are again just to help you graph it a little bit better. So let's plot these points. So we've got 1, -1. At 2, we've got negative 0.66. So that's like maybe here. 3, we've got negative 0.6. 4, we've got negative, I'm gonna move these down a little bit. At 4, we've got negative 0.57. Okay. So what are our thoughts based off of the graph? Do we think this is going to converge or diverge?
Converge.
Diverge.
All right, well, I heard both. So when we say diverge, do we think it's going to positive infinity or negative infinity?
Positive infinity.
Okay, so we think this is just going to keep going up forever, and that's why we think it diverges. Okay, so for the folks who said converge, why do you think it's going to converge, and what value do you think it's going to get close to?
It's get close. It does. I believe it gets closer to 0, but I don't think it diverges because it's always going to be on the negative. It's not going to be able to go all the way up to the positive y-axis.
How do you know it's always going to be negative, Karen?
Because we're subtracting 1 to the n, and the n's always getting bigger. It's never getting smaller.
Everybody hear what she just said there? That all of the terms that you get out are always going to be negative. And I think that's actually a really important observation here, okay? So when you look at formulas, part of what we're going to be doing towards the end of today is thinking about what can it get to, what can it never get to, okay? So it's always going to be negative in this case. So I would say folks that said it was going to diverge, it's never going to go above the x-axis, which means it's never going to go to positive infinity, okay? So I think we might have a question about whether it converges, but maybe we're not sure based off of the picture what value. Like, is it getting to 0? Is it getting to negative 0.1? Like, how do we know? Okay. And so what I'd like us to do now is we're going to set up the limit notation again. And from the limit notation, we should be able to figure out what value it converges to. Okay. Because the number that comes out is the value that the a sub nth term converges to. So we have the limit as n approaches infinity of the equation, n over 1 minus 2n. And I'm going to plug in infinity, 1 minus 2, infinity. And so I'm going to get infinity over negative infinity, which is a case for L'Hopital's. That means that I need to take the derivative of the top, which will give me 1, take the derivative of the denominator, which is negative 2, and then, oh shoot, there's nowhere to plug in the infinities, but that's fine, because it means that no matter what it is, the n value, it's going to go to negative 1/2. So we were correct. Some of us were correct in our initial guess that it converges, and it in fact converges to negative 1/2. Okay. Now, if I had spaced out my graph a little bit better, what I might have seen is that if I draw this line y equals negative 1/2 here, it's almost like, what is that word for that? Like, you guys learned about a description for when things get really close to a certain line but never cross it.
Asymptotes.
Yeah, so when you're learning about horizontal asymptotes, what you're really saying is, what does it get to when you go to infinity? Or what does it get to when you go to negative infinity if you're not dealing with sequences, okay? So this value, if you had looked at the original equation, n over 1 minus 2n, without L'Hopital's, you might have been like, oh, I know that's gonna have a horizontal asymptote of negative 1/2. That is your converging value. Okay, so it's the same as that horizontal asymptote of y equals negative 1/2. Pretty cool, huh? All this stuff that you learned before and was like you learn about it one way, and now it's like there's just so many other ways to describe that same feature on a graph. Okay, so let's do one last example here. We've got a sub n equals 5n over e to the 2n. Now, let's go ahead and find the first 4 terms. So do me a favor and just write out, like, what is it in the exact form, and then turn things into a decimal. So what I mean by that is for a sub 1, you'd write like 5 times 1 over e to the 2 times 1, or 5 over e to the 2, right? That's your exact number. And then when you put it into the calculator, you should get about 0.67 for that. So that would be your one that's going to help us graph it, okay? So go ahead and do that for a sub 2, a sub 3, a sub 4, and start plotting those points. You can use whatever scale works best once you see the point values on part B on that grid. You should be getting some really small values here, and that's okay. All right, I know that a sub 4 is going to be super hard for us to graph, but I think it'll give us at least a good imagination of what we're doing here. Maybe let's call that first 1.7. Yeah, we've got 1, 2, 3, 4. Okay, so if we start plotting these points at 1, we get about 0.67. At 2, we get about 0.18, which is about here. At 3, we get 0.04, so that's like real close there. And then at 4, we get basically at the x-axis as far as our like sort of human eyes on this scale can go. All right. So based on these values that you're seeing, as well as the diagram, what do we think? Converge or diverge?
Diverge.
Okay, and if it converges, what value?
0.
0, yeah. I mean, it looks like it's getting pretty close to 0. Are you going to be able to get negative values out? Let's use Karen's thinking from earlier. I really like that. Can we get negative values out?
No.
Yeah, we can't get negative values out. So it seems like it is getting closer and closer to 0 already. With the 4th term, it was so hard for us to graph that like we would have to change the scale for the rest of the terms, right? So yeah, I would say it converges, and it probably converges to 0. So let's confirm that with our limit notation. So the limit as n approaches infinity of 5n, gosh, 5n over e to the 2n, we're going to get infinity over infinity, which means we have to use L'Hopital's, right? So we'll take another limit with the derivative. The numerator goes to 5. What does the denominator go to?
Two e to the 2n.
Yeah.
1/2. Oh yeah, that's right.
Yeah, we're taking derivatives here, right? So we just bring that, we multiply it. So we're using chain rule. What's the derivative of 2n? It's just 2. So we've got 2e to the 2n. And now when we plug in our infinity, we'll get 5 over infinity, which itself is undefined, but because we're taking a limit, we know that it gets close to 0. And so yes, we have confirmed our answer from the previous part, that as we go infinitely out in this sequence, we will approach a y value of 0, that all the terms will get really close to 0 towards the end, okay? All right, so let's do this. Let's take a break right now. It's 10:25. Maybe we could come back at 10:32, and then we'll pick up with the second half of this. All right, so let's be back at 10:32. Okay. So for this second half of class, we're going to take a look at this idea of convergence in a little bit more of a mathy way, okay? And actually, I think from the earlier conversation about whether things could be positive or whether they have to be negative actually leads very well right into this section. And that's the kind of thinking that we're looking to do for perhaps a little bit more of a mathy view on convergence, okay? So for any sequence, a sub n, now this brackets around the a sub n, usually that is a pretty common notation when we're writing about sequences in general. You'll have the little brackets around there. But the a sub n part should also be a clue that you're looking at sequences. So we want to talk about sequences in terms of increasing and decreasing, okay? So let me just kind of divide this into sort of the top half and the bottom half. So for the first 3, let's read through those. It says, we will call the sequence increasing if a sub n is less than a sub n for every n. Okay, what does this mean, this statement right here? A sub n is less than a sub n plus 1. Any ideas? Or is this the weird thing where you're talking and I can't hear you?
I mean, I guess nobody's going to answer, so it's for every n we just add 1. So it means that I don't know.
Like if
Okay.
it's
I think
positive and if the sequence is negative, or if it's because I believe like a sub 9, like I mean, and if it's like greater than, I'm just thinking if like I would have plugged in numbers, like it would be like if it's like positive, if it's going up.
It's always going to be less than on the left side.
Well, I kind of like your idea of plugging in numbers, but maybe what we could do is plug in numbers for n, okay? Because this is talking about any sequence. So let's say that we had a sub 9. That would mean a sub 9 has to be less than what?
A sub 10.
A sub 10, right? Because 9 plus 1 gives me 10. Okay, well, let's pick some other numbers. What if I had like a sub 100? What would that have to be less than?
A sub 101.
A sub number of Dalmatians, right? Less than 101. So it doesn't mean that 100 is less than 101. It means the 100th term is less than the 101st term.
Mm-hmm.
Or going back to our earlier example, the 9th term is smaller than the 10th term. Okay? So when we realize that if we look at every single term in the sequence, and this has to be true for every single term, okay? If the current term, your a sub n, is less than the next term, then you end up with a sequence that is increasing, okay? Let's think back to our first example, the Fibonacci sequence. Increasing or no?
Yes. Mm.
It has to be true for every term?
Has to be true for every single term.
No.
No.
No, why not? What makes it untrue?
First two terms.
The first two terms, right? Because 1 is not less than 1. So that, even though it's only that little bit, makes it not an increasing function, okay? Now we can use the same description to look at decreasing functions. We call the sequence decreasing if, for example, a sub 9 is greater than a sub 10, or a sub 100 is greater than a sub 101 for every single n, okay? So with this increasing and decreasing has to be true for every single term. And because we're not going to sit and write out like an infinite number of terms, it's really important that we're able to identify some patterns like Karen did earlier, where she was like, well, it's not ever going to be positive, so I know that it has to stop at some point, right? So that's sort of, we need to use some of what we know about numbers in general to help us explore whether sequences are increasing or decreasing, okay? Now, if a sub n is an increasing sequence or a decreasing sequence, so it could be either one, increasing or decreasing, okay? We have a special name for it. It is called a monotonic situation, okay? So monotonic means it's always increasing or it's always decreasing. That's going to be the first part of what we're looking at in the next question, okay? Whether things are increasing or decreasing. The next 4 bullet points there, or the next 3, 4, 5, and 6, talk about something called bounding, okay? So if there exists a number, m, okay, so m is just a random number. It doesn't even have to be in the sequence, okay? M is just a number. If there's a number m such that m is less than or equal to a sub n, like m is smaller or equal to every single term in the sequence, then we say the sequence is bounded below. The number m is sometimes called a lower bound for the sequence. So let's go back to this Fibonacci sequence we looked at, 1, 1, 2, 3, 5, 8. We decided it's not increasing. And I think we can also decide it's not decreasing. So that makes it not monotonic. What is the lower bound for the Fibonacci sequence?
0.
1.
Okay. It is actually, so technically the Fibonacci sequence actually starts with 0, by the way, PS. Nobody ever really uses that, but it does start with 0. That's how you get 0 plus 1 gives you another 1. So yes, 0 could be the lower bound. If we had it the way it was written, we could say 1 is the lower bound. What else could be a lower bound?
1/2.
Not 1/2, because that's greater than 0.
-1.
Negative, yeah, any negative number would work. -1, sure. So we can have more than one lower bound, but usually we like to pick, quote unquote, the best one. Okay, and what we mean by the best one is that it is the one that is like closest to that lowest value. So it makes it's important if we're looking at this lower bound, if we call it 0, that's probably the best one. We could also say -100, but that might not be as effective in whatever we want to do with the sequence afterwards. Okay, so we really want to try and find that like sweet spot, like what is the biggest lowest bound, so to speak, the biggest lower bound, and in that case it would be 0. Now, just like there could be a lower bound, sometimes there exists a number such that this, and we'll call this number capital M, but capital M is actually bigger than every single term in the entire sequence. If there exists this kind of number, then we say that the sequence is bounded above. And this number M is sometimes called an upper bound for the sequence. So we've got a lower bound and an upper bound, and those are different from like when we're integrating and we have like the number on the bottom and the number on the top, okay? Now, if a sequence happens to be bounded below and above, then we call that sequence bounded. We don't even say bounded below or bounded above, we just say bounded, okay? All right, so that's some vocab, but now let's apply this vocab to some examples where we're going to take a look at whether they are monotonic or not, or whether they are bounded or not, okay? Okay. So example 6, we have a sub n equals negative n squared. Okay, and to clarify, I'm not taking negative n and then squaring it. I am rather squaring it and then making it negative. And my quote unquote starting point, I'm going to start with the value 0 for n. So I'm going to start at 0 and keep putting in like numbers like 1, 2, 3, 4, 5. Okay. So let's actually, before we answer these questions, one of my strategies tends to be, if I want to know whether it's monotonic or not, I actually just write out a few terms in the sequence. Okay, I write out a few terms, start to see what's happening, because it makes it a little bit more concrete for me rather than just being like, ooh, what's happening, okay? So if I plug in 0, I'm going to get 0. If I plug in 1, what am I going to get? And when I plug in 2,
-4.
and then -9, and then -16, and so on and so on, okay? Based on those numbers, and for this particular sequence, I think it's very easy for us to identify that this is a decreasing sequence, which means that it is monotonic. right? Because if it's decreasing, it's monotonic. But not all sequences are that easy to tell whether they're going to be decreasing forever or increasing forever. And so what I'd like to also show us is sort of a more algebraic way of looking at this, which is we're going to use the idea, if we think it's decreasing, what that means is that a sub n has to be greater than a sub n plus 1. Right? That was from our definition earlier. If we think it's decreasing, this should be true no matter what we pick for n. It could be the 9th term and the 10th term, or it could be the 100th term and the 101st term. It could be the 1,000,000th term and the 1,000,001 term, but it always has to be true that the one that comes before is bigger than the one that comes next. So let's plug in to our explicit formula here. So every a sub n is just negative n squared. How would I write this for a sub n plus 1?
Negative n squared plus 1.
Negative n squared plus 1? I'm going to say no on that.
Yeah, I forgot it's all below the, yeah. It's always all sub under the a, I guess. So
how do we fix that? Because this is a really common mistake, right? We just add 1 to the n, but that's not what we're doing. All right, so Broy, I love your response. We're going to actually say in everywhere we see an n, we're replacing that with n plus 1. That means that we're going to take n plus 1, we're going to square it, and then we're going to make it negative. So I don't want to do this, but instead I have n plus 1 squared, and then I make it negative, right? Now let's talk about these sort of in terms of general numbers. If I take n, which is a positive number, and I square it, I get a positive number. But then I'm going to make it negative. So I get on this side, I have a negative number, okay? Now, when I take n plus 1, and is that bigger or smaller than n? Yeah, yeah, it's bigger, right? N plus 1 is bigger than n. So when I take n plus 1 and I square it, is that going to be bigger or smaller than n squared?
smaller.
Larger.
Yeah, n plus 1, when I square it, will be bigger than n squared. But then I make them both negative. So I have a negative number, and is that greater than the negative of a larger
Yes.
negative number? And it is, because if I like picked a random number like -4, a larger number, 9, but if I make it negative, -4 is bigger than -9, right? So even though we weren't able to write out every single term, we can use this thinking, this sort of like what we know to be true about numbers. What happens when we square them? What happens when we make them negative? Which direction on the number line is it going? All of that kind of thinking helps us know for sure that this sequence is decreasing, and therefore it's monotonic, okay? All right. Now let's think about whether it is bounded, okay? So let's check first, is it bounded below? Like, is there a number that is smaller than every single number in the entire sequence?
No.
No, there's not, right? And maybe as a reason we could say because the numbers trend towards negative infinity. Now that means it's not bounded, but let's just check, is it bounded above? Okay. So is it bounded above this particular sequence? Is there a number that is larger than every single number in the sequence?
Yes.
Yeah, right? And now it doesn't have to be bigger. It could also be equal to the largest number in the sequence. So I would say that yes, it is. And we could say that negative n squared has to be less than or equal to 0. And 0 would be considered that top bound or the upper bound, okay? So overall, it is not bounded, but it is bounded above. It's just not bounded below. All right, now we didn't do a diagram for this, but what are you folks thinking? Does this sequence converge or diverge?
Diverge.
Yeah, diverge. So let's just do our little limit. And we're going to plug it into negative n squared. And I think once we do that, we get negative infinity squared, which is going to be negative infinity. And that definitely diverges. Okay.
Can I ask a clarifying question?
For sure.
So when you were trying to prove algebraically whether or not it was monotonic,
Mm-hmm.
what you would do is you would set up your your sign of whether or not it's greater or less than,
Mm-hmm.
and then you would take the original equation, and on one side you would just plug in n, and then on the other side, wherever you had an n, you would plug in n plus 1.
Correct.
Okay.
Mm-hmm.
And then if it is monotonic, it will only be bounded upper or lower. It will never be bounded, right?
Ah, yeah. Mm-hmm.
Okay. Yeah, I think that's all I got.
Okay, cool. All right. Oh. Also, thank you folks for being so patient and so kind about my endless typos and mistakes in my answer keys recently. I had about 2 weeks between the end of the spring semester and the start of our summer school class, and was actually like able to really get ahead in terms of planning for our summer class. And then I just didn't get to sort of the pieces where you see me starting to fall apart. So thanks for going with the flow here. But this is example number 7, not example number 6. And did I just copy it more than one time? Yep, sure did. We don't even need this one. Extra paper, sorry folks. Okay, we're going on to the real example number 7 here. So we've got a function, or a sequence rather, a sub n equals -1 in parentheses, and then we're raising that to the power of n plus 1, okay? So let's take a look at whether this is monotonic or not by writing out the different terms, and then let's compare our a sub n and our a sub n plus 1, so we can kind of be sure that it is the answer we think it is. So if I find a sub 1, that means I plug in 1 everywhere I see an n. What value is a sub 1?
1.
It is 1, yeah. A sub 2 would be -1. A sub 3 is back to 1. A sub 4, a sub 5, a sub 6. So based on that, what do we think? Monotonic or not?
No.
No, right? We are actually, this is a specific kind of sequence that we're going to take a look at, where it is alternating, and the alternating means the signs alternate, okay? So we can see from this that it is not monotonic because the signs alternate. We fluctuate between 1 and -1, 1 and -1, okay? But how might we approach this in sort of a more mathy way? Well, we could say if I have a sub n and a sub n plus 1, is there a clear relationship that I can construct between a sub n and a sub n plus 1. So if I plug in a sub n, I will get -1 to the n plus 1. And if I plug in n plus 1, I'll get -1 to the what?
To the top.
N plus 2.
Yeah, let's write it out as n plus 1 plus 1, which does in fact become n plus 2, okay? So -1 to the n plus 1 versus -1 to the n plus 2. Is one of those always bigger or smaller than the other one?
Yes.
Which one is always bigger or smaller?
Oh, never mind. No.
No. Okay. Yeah, because it really depends on what n is, right? If I pick n as an even number, the relationship is going to be one way. But if I pick n as an odd number, the relationship will flip. So because I can't have a set like one is bigger than the other, we could say there's like no set rule here, like it's not greater than, it's not less than. That further confirms that it is not monotonic. Okay. So James, to kind of follow up with your earlier like process, I would say that if you have an inkling, like you think it's decreasing, put in the proper sign. If you think it's increasing, put in the proper sign. But if you think it's neither, kind of like go through this. You don't have to put a greater than or less than in there if you're not sure. Okay.
Okay. Just plug it in, kind of evaluate.
Yeah. Okay. All right, so let's take a look at whether this one is bounded or not. What do we think? Is it bounded above? Is it bounded below?
It's just bounded.
What would the upper bound be that makes you say that?
1.
Yeah, it's going to be 1, right? It is bounded above. I would agree that it has, like, we could say big M equals 1. Gosh. And it is bounded below using similar reasoning where that little m equals -1, right? So we can say that, yes, this is bounded. It doesn't get any bigger than 1. It doesn't get any smaller than -1. Okay. Now, I know some of these early examples are like so obvious that you're kind of like, well, why are we doing all the extra stuff? But it's really just to kind of set forth like being really explicit about our kind of thinking so that when we apply it to different scenarios, we can really understand like, okay, I didn't just know how to do sort of this one level of problem, but I developed a system of thinking so that I can access a lot of these different types of problems, okay? So what do we think? Does the sequence converge or diverge?
Converge.
What value does it go to if you say converge?
Would it be in between 1 and -1?
Okay, so when we talk about converging, and I totally get where you would say that, right? Because you're like, well, maybe it converges to 0, like it's like halfway in between. But when we're looking at whether things converge or not, it's like all of the end terms sort of get closer and closer and closer to that value.
It doesn't get close to anything because I believe if we keep adding numbers, it's just gonna be either negative or positive. It's never a solid, like it's never one specific number it's getting close to. It's either
That's
or.
true.
Yeah, exactly. So we might be tempted to say 0, but it does, like you've all recognized, that it kind of just keeps flip-flopping forever and ever. And if we go back to our limit, And we say, all right, what happens when we plug in infinity into our explicit formula? We're either going to get 1 or we're going to get -1. But it depends on our n, right? Kind of the same thing we said about is it monotonic or not. It depends on the n. And it's only going to converge if it doesn't even matter what the n is. As long as it gets really big, it's trending towards a number. So in this case, we're going to say that this sequence diverges because it sort of flip-flops between those two. Okay. All right, let's take a look at this one. Okay. So we have a sub n equals 2 over n squared. And just to change things up, we're going to start at n is equal to 5 and then pick positive integers greater than 5. Okay. So let's see. Is this monotonic or not? Let's start actually with this like a sub n and this a sub n plus 1. Okay. So if I have a sub n, it's going to be 2 over n squared, right? What about if I have a sub n plus 1? What is that expression going to look like?
Two over n plus 1 square.
Good. Well, there you are. I haven't heard from you all day.
Yeah, I have a lot of noise, so.
Okay, n plus 1 squared. Okay. So let's see. They have the same numerator. So let's look at what happens with the denominator. So I have 2 over a number, right? 2 over some number. Now, n plus 1 is going to be a bigger number or a smaller number than n?
A bigger.
A bigger number. Okay. And then n plus 1 squared, is that going to be a bigger number or a smaller number than n squared?
Bigger.
It's going to be bigger. Okay, so we have a denominator that's a number, and then we have another denominator that's a bigger number. Is there a relationship that we can state between the two sides of this?
Yes, a sub n gonna be larger than a sub n plus 1.
Yeah, exactly. This left-hand side, 2 over a number is always going to be bigger than 2 over a bigger number, right? This side is more like, oh, you know, you have like maybe you're an only child, maybe you have one sibling, right? There's like you're not having to share your time and attention with that many other people. But if you take a look at perhaps some bigger families, I'm not saying this is true for all bigger families, I'm just trying to come up with a comparison. Maybe you feel like if they're like you have like 12 siblings that maybe you get a little bit less attention, right? It's like you only have your 2 parents and then you know a little bit less attention. So this bigger denominator means that the fraction on the right hand side is actually the smaller value. Okay, and so because we've shown that a sub n is always bigger than a sub n plus 1, we can say that this is a increasing or decreasing sequence.
Decreasing.
Yeah, it is decreasing. And that means that it is monotonic. Okay. All right, now, is it bounded below, or is it bounded above, or is it both? So,
Both?
okay. Tell me how you know it's bounded below. Like what is your little m?
My little m, I believe, would be 0.
Yeah, because we're squaring numbers. And so we know that a positive number divided by a positive number will always be positive. Okay. So we know that it has a lower bound of m equals 0 because it is always positive. Right? So 2 over n squared is always positive. Now, how do we know that it's bounded above?
Because it will never go beyond a sub 1.
Say that again?
It gets smaller and smaller and closer to 0 because we're squaring it.
Ah, okay. So our sequence is decreasing. That means my first term is the biggest one.
So
Right.
the larger m gonna be 2 over 25.
So because it's decreasing, we know that a sub 5, which is our sort of starting term here, because we're starting with n equals 5, is 2 over 25 is the largest term in the sequence. Okay, so we could say that big M is 2 over 25. And so because we have a bounded below and bounded above, we can say that it is bounded, bounded. Okay. All right.
Can I ask something on that?
Uh-huh.
So is it safe to say that if your general equation converges, your bounds, the equation will always be bounded between A1 and where it converges?
Let's maybe wait a little bit to draw that conclusion.
Okay.
Okay. All right. So for this question, this sequence, does it converge or diverge? I think we probably can guess it converges, but let's just be sure here. So we get 2 over infinity squared, which is 0. And so this sequence does converge. Okay. So James, would you mind repeating your question one more time?
I was just wondering that if your general equation converges to a value, if that is part of the limits of where it's bounded, if it's bounded from a sub 1 and to where it converges.
Yeah, that converging value will be one of the bounds. It sort of depends, like, is it an increasing function or decreasing function? Right, because if it's decreasing, it will be the bottom or the lower bound. But if it's an increasing function, then it will be the upper bound.
Okay, so depending on which way it's going, we'll flip the convergence in the A1.
Right. And yeah, Patrick, so with sequences and what we're going to be learning for the rest of chapter 11, which is series, we're only looking at the input being positive integer value. Okay, so n will have to be 0 or bigger. So we're not looking at the negative side. All right, we got one last question here before we take a look at a theorem. Okay, so this one, we've got a sub n equals n cubed over n to the 4th plus 10,000. And we're looking at n is greater than or equal to 0. Okay? So let's figure out if this is monotonic or not, right? What do we think? Looking at that sequence.
Oh,
Decreasing?
Okay, we think it's decreasing. What makes you think it's decreasing?
Because the numerator just or the denominator keeps getting bigger and bigger and bigger.
Okay. Any other thoughts about whether this is increasing or decreasing?
oh well, yeah, it's most likely decreasing. Because if we were to add the 1 to the n, it's gonna a sub n is greater than a sub n plus 1.
And the n is negative. Sorry, I take that back.
Okay, so our initial guess is that it is decreasing because it would go this way, right? So that's kind of our initial guess. And I think that's not a bad place to start, right? Because you have a power on the bottom that's bigger than the power on the top, okay? But let's do this. If we could maybe have a few different people plug in some numbers. If anybody has their calculator handy, maybe we can get a value for a sub 1, a sub 2, a sub 3, a sub 4. Let's kind of see what we get for those, okay? So if you have a calculator, maybe pick one of those and then either type the number into the chat or something, and we can kind of get those numbers squared away. All right. A sub 2, we've got an 8 over 10016, which I think is about 0.0008, I think, about. Okay, a sub 3, we've got 2, 4, 7,
Decreasing.
over 27. 27 over 10081, and that's about 0.00268. Okay. A sub 4, I don't have the fraction, but it's about 0.00624. This one is about 0.0001. Well, I mean, even with those first 4 numbers, are those increasing or decreasing?
They're increasing.
They're increasing, right? Well, as it turns out, if you kind of go, the numbers are going to increase for a little bit, and then at some point, they're going to start to decrease, okay? So your folks' guess that, like, on the whole, it's going to decrease is true, like overall in the big picture. But we have some exceptions here that for the first few terms, actually increase, okay?
So that means it's not monotonic?
Exactly. That means it's not monotonic, okay? Now, what I'm about to show you is, or remind you of rather, is just a little bit of a throwback to Calc 1 to think about, like, if you wanted to find out for sure whether things are monotonic and you didn't want to sit and plug in like a whole bunch of numbers, okay? And if you graph this n to the third over n to the fourth plus 10,000, the numbers are such that, like, even when you zoom in, it just looks like a flat line. So it's really hard to tell from the graph. And it's kind of hard to tell from the numbers, right? These are sort of weird numbers to plug in. So what you can do to find out whether things are always increasing or always decreasing, okay, so another sort of strategy you can do is you can go back and you can find critical points using first derivatives. Okay. Now, that would mean we'd find the derivative of a sub n. Okay, so you'd find your derivative. You'd set it equal to 0 and solve for n. All right. And then if your slope is positive, that means that your sequence is going to be increasing. But if the slope is negative, it means the sequence is decreasing. Okay, so a positive slope or a positive derivative would mean that's where your sequence is increasing. Whereas a negative derivative, that would indicate that your sequence is decreasing. Okay. So when we're thinking about like how we could find out for sure, we could take the derivative. In this case, we would need to use the quotient rule. We would set it equal to 0, solve for n, so we know sort of like where the slopes are 0. And then we could plug in numbers in between and find out whether the slope is increasing or whether it's decreasing. And it turns out that when you do that for this particular sequence, that between 0 and 13, the function is actually increasing. So that's why these first 4 values that we've seen are getting bigger and bigger and bigger. They would keep getting bigger until we got to a sub 13. But then after that, a sub 14 all the way to like the very last ends of this infinite sequence, it would be decreasing. Okay, but it goes back to that definition of monotonic, that it has to be always increasing or always decreasing. Okay. Now, are there any questions about that before we talk about the boundedness?
So you took that first derivative of that whole thing, you set it equal to 0, and the answer that you got out was 13. And then so that was the point where it stopped increasing and started decreasing?
Yeah. Okay. So remember, critical points are nothing more than like a maximum or a minimum on a graph, sometimes an inflection point. So that's where things start being increasing and start being decreasing. So, okay. Now, let's sort of take a step back from like this very big thinking sort of thing and revisit whether things are bounded or not, right? So rather than answer like, is it bounded above or is it bounded below, like, are there any restrictions you see based off of the formula in terms of numbers coming out of that function?
It will never be higher than a sub 13.
Okay, it will never be higher than that. I would agree. And is
the lowest.
Do you mean a sub n, Roy? Yeah, okay. Yeah, it's never going to be bigger than 1. Tell us why that is. Yeah, that denominator is always going to be larger, right? So my output value is always going to be less than 1, right? So we know that it's bounded above by 1. What about, is there a lower bound for this?
Would it be 0?
Yeah, and a sub n is never smaller than 0. And how come it's never going to be smaller than 0?
Because n is equal to or less than, I mean, greater than or equal to 0, and it seems to have the smallest a sub.
Yeah, okay. So Carlos, that's a really great observation. This formula, given my n greater than 0, means that I'm always going to have a positive output, okay? So this is because a sub n is always positive, right? When I plug in numbers, it might get really small, but it's never going to be negative. So because it is bounded above by 1 and below by 0, it is considered bounded, okay? So our question then is, does it converge or diverge? And let's take a look at that. So if we take the limit as n approaches infinity of n cubed over n to the 4th plus 10,000, we get infinity over infinity, right? That's a case for L'Hopital's. So we take another derivative. We get infinity over infinity. So we have to use L'Hopital's again. We get, where are we at? 6n over 12n squared. All right, we need L'Hopital's again. I think this is the last one. We get 6 over 24n, which gives us 6 over infinity, which does give us 0. Okay. So we can say that this sequence converges to 0. Now, I think it was James, this might actually be an exception to what we were talking about earlier, in that this one is not monotonic, and yet it converges to one of, like, it doesn't always go up or it doesn't always go down, but it does converge to a particular value. I think it's more, it does fit, like the end part after after a sub 13, it does fit with your pattern, but before that it didn't quite. Okay.
So would you have to test it by seeing if there are any critical points?
So we're going to take a look at a theorem now that I think might clear that up a little bit. Okay. So here is a theorem about the conclusions that we can make, along with a very large in bold caveat about when you cannot make these assumptions. Okay. So if you go back over examples 6 through 9 later, you'll notice that in the cases where a sub n was bounded and monotonic, okay, we answered first, is it bounded, is it monotonic? If we got a yes for both of those, then we were able to find that a sub n converges, and we were able to find the value that it converges to. So let's take a look at that. Example 6. It is decreasing, so it was monotonic, but it wasn't bounded. Example 7, it was not monotonic and it was bounded. But this one, example 8, it's monotonic and it's bounded. We see that it's both of those. According to this theorem, we should know from that it converges. Okay, so if it's monotonic and it's bounded, you got a converging sequence. Does that part make sense to folks?
Yes.
Yeah, okay. So that's what this theorem says. But here's what I do not want us to confuse this with. It doesn't mean that if you use the limit and you find out that it converges, that it's then bounded and monotonic. So it doesn't go the other way. All right, let me say that one more time. If your sequence is convergent, it does not mean that the sequence is bounded and monotonic. Okay, it's a one-way street. You can only say if it's bounded and monotonic, then the sequence is convergent. But you cannot flip the order and say if it's convergent, then it's bounded and monotonic. And that is, my screen sharing stopped working, but that is why example 9, if you look back at example 9, it converged and it was bounded, but it was not monotonic. Okay. So just because it converges does not mean it's bounded and monotonic. And that is where we're going to stop today. Okay.
Can I ask one more question on number 9?
For sure.
Number 9, when you knew that it was decreasing at first and then increasing, what was kind of the signal that you knew that it was gonna increase and then at some point it was gonna start decreasing? Was it that plus 10,000 that you sat there and you're like, oh, okay.
No, you don't always know. You just have, it's more like number 9 is like a cautionary tale.
Okay.
A cautionary tale that you never quite know. There are situations where you have to be careful.
Okay, so just with exposure, it was kind of like instinctual for you to be like, oh, okay, let's find out where it's gonna.
Yeah, it's one of those terrible situations where I can't say like, oh yeah, it's the 10,000, and every time you see that, then you should be careful.
So then would it be safe to say that like if we came into where it was like it was a general equation that was something kind of gross looking, that if, just take the derivative, see if there's any critical points. If there's not, then you don't have to worry about it going up and down.
Right, exactly. So those critical points, I think, are more helpful in saying, okay, can we know for sure that it is always increasing or always decreasing? Yeah.
All right, thank you.
All right. So almost 11:30 on the spot. I'm going to stop sharing the screen right here. I'm going to stop recording.